A good day to all of the electronic participants in today's ALTA session. This talk is on the important subject of the reduction and possible substitution of cyanide for the recovery of gold. MPS, or Mining and Process Solutions, a company that I'm a director of, has spent the past 4 years doing intense research on our glycat process, which is a method of combining glycine leaching with reduced or starved cyanide systems. This has the unique twin properties of not only decreasing cyanide consumption from the transition metals like copper, but also leaching and recovering them as well. In the meantime, the system leaches gold at the same time, and repeated testing shows that there is no free cyanide present within the operating system. We have also done considerable research on several other glycine gold leaching combinations that are cyanide free. Here's some definitions that are included. Their glyleach refers to the leaching of metals with glycine alone. And GT, or we call it, is a mixture of glycine and thiourea used to leach gold under acid conditions. And glycine is a dual lixiviant system. The second lixiviant can include cyanide and many other non-cyanide things. So here's a quick outline of the talk today. We're going to first of all talk about glycine leaching alone, and then under that also with non-cyanide additions. And then we're going to talk about glycat, which is glycine leaching in cyanide-starved systems. Okay, here is some of the chemistry of our cyanide-free systems. I do not propose to go over the equations during the talk, but present them here for your future reference. So at any rate, there are reasons for adding various additives to glycine, and they are: one, we get accelerated leach rates of gold. Secondly, we can establish a cyanide-free leaching system. And three, we get high leach rates at ambient temperatures. Glycine on its own can leach gold very slowly, but at high temperatures and high pH, it can become very aggressive. And under certain conditions, potassium ferric cyanide, potassium permanganate, can aggressively oxidize gold and make it available to be complexed by glycine. Okay, glycine is the simplest and most common of the amino acids. It is a vital part of every human's life cycle and is a non-toxic reagent. It has been known for some time that gold is mildly soluble in glycine, but it has also been reported that the reaction in the presence of air is very slow. However, recent work at Curtin have shown this to be accelerated by both pH and temperature. Now, cyanide is an exceptionally good reagent. It really works for gold, but there are environmental concerns about cyanide toxicity. There are a lot of alternates offered on the open market, and these include things like thiourea, glycine, thiosulfate, thiocyanate, and the halides, which include the bromides and the iodides. Unfortunately, most of these things, plant adaptability to the various flow sheets is a major problem. But of these alternates, recently glycine has been shown to be a promising alternative. Now, there's been a new paper published in Minerals Engineering, and it's the leaching and recovering of gold from an ore in cyanide-free glycine media. The work has been done at the Pori Research Center of Metso Autotech at Pori, Finland. So it's a very independent validation of the work done by Eckstein and Oraby at Curtin University. What the paper concluded, that the dissolution of gold in a gold ore was partially dependent on glycine concentration, but not radically. Work by Curtin showed a very dramatic correlation between concentration and leaching rate, but that was using gold foil rather than a gold ore. The work also showed that gold extraction is highly dependent upon temperature and pH. It showed that addition of activated carbon to the pregnant leach solution can provide a 100% recovery of the gold that has been leached, and it surprisingly gave a superior dissolution compared to straight cyanide with an epithermal ore that did contain significant gold as tellurides. Now, what we have here is a graphic depiction of the effect of pH and temperature on the solubility of gold foil and glycine. And the vertical axis is pH, the horizontal axis is temperature. And think of it as a contour map showing recovery rather than elevation. And the portion up in the upper right-hand corner is where we have to be when we're trying to leach with this material. Right, now here's a graph that was put out within the paper, and it shows two independent agitated leach experiments using pure glycine, which has been heated and the pH adjusted, and using cyanide at 0.75 grams per liter. Both suspensions were strongly agitated, and it shows that the heated and high pH glycine, this is 60 degrees C, the pH of 12, with a superior recovery to straight cyanide. There's what appears to be a much better finish to the leach curve, and the authors of the paper ascribe this to the fact that the tellurides must dissolve much easier in glycine than in cyanide, and accounts for the better finish. Okay, now here we're going to look at two other cyanide leaches. Now these are of different strengths. We have the blue dashed line is 50 parts per million cyanide, the red dashed line is 300 parts per million cyanide, and the red line is glycine itself. And this is a result from a free milling gold ore from Nevada. Right. Another glycine permanganate leach profile contrasts one cyanide result, one cold glycine result, and a combined glycine permanganate. Note that the cyanide and the glycine permanganate gave equal results after 24 hours, and then after that both suffered from mild preg robbing. Again, a free milling ore from gold ore from North America. Now we also have the GT process, which is a mixture of glycine and thiourea. Here we're leaching gold under acid conditions, pH 1.5. We have gold, it's a oxidized, a bio-ox product, which is very acid. We're leaching it at the acid, at the pH that it is produced at 1.5. And we add thiourea, and we see we're getting up into the mid-80s when we add 1.5 grams per liter ferric. And ferric is an oxidant to put the gold into solution. Now, this is a modification of an old method that has never been used commercially because of the very high reagent consumption caused by excess ferric. And if you don't have ferric, the gold doesn't go into solution, but it destroys the urea that makes the process uneconomic. We have modified it by the addition of glycine, and it does constitute a cyanide-free process to deal with acid leach products and can save the considerable cost of lime to neutralize and raise the pH to the safe point around 10. Glycine possibly prevents the oxidation of the thiourea by combining with the ferric to form ferric glycinate. And we're doing a great deal of research at the moment on this very interesting process. We'll now have a look at the BICAP method. And there, once again, we list the equations for you to see, but we won't go over them in detail. But if you look at the start, you'll see that copper forms complexes with both glycine and cyanide. And in the first two equations, it can be stated that the glycine complex is more stable than the cyanide complex. I will not go over the equations, but they're included here for completion. It's also worth noting the existence of the copper-1 glycinate. The copper-2 glycinate is a good oxidizing agent and is able to attack and leach gold and form gold +1. And this oxidation forms the cuprous glycinate. The anion is oxidized back to the cupric state when it's exposed to air. Again, I'm not going to waste my time reviewing the equations, which are multiple, but they're included for completeness. Now, here's a rather a complex graph, and this is tank leaching with two domains from the same mine. And note the solid colored curves represent gold extraction, while silver is represented by the dashed curves. And all experiments have a common time period of 24 hours. Vertical axis in the graph is recovery. Horizontal axis is cyanide use in kilograms per ton. And you'll notice that we're working in the region from 0.3 of a kilo per ton down to around 1/10. So in the first domain, the light blue line is no glycine, which you can see there, and you can see the silver equivalent down below it. The orange line is 0.32 kilos per ton glycine, which you can see that's the best in the domain and the best of both series at 0.10 kilograms per ton sodium cyanide and 0.32 kilograms per ton glycine. The gray is experiments represented at 0.6 of a kilo per ton, and the yellow at 1.25. Now, domain 2, the dark blue line is no glycine, and the green line at 0.12 kilos per ton of glycine is best in the domain at 0.26 kilograms per ton cyanide. These are rather remarkable things in that both of the glycine products show notably better recovery. The value of the saved cyanide is not much, but the possibility to increase gold recovery in a large milling complex by 2 to 3% is, of course, of great interest. It's even more interest if the predicted reagent consumption is reduced. And we're doing an intensive series of bottle roll tests on these samples now. Okay. This is glycat leaching of gold ore with minimal copper. And I contrasted the leaching with straight cyanide at a much higher concentration. The yellow curves are glycat in a 6-meter column. The blue curves are cyanide in a 1-meter column, and the greenish curves are glycat in a 1-meter column. So in every instance, the glycat outperforms straight cyanide at a much stronger concentration. So it's a very very interesting thing. All right, here's a pilot plant that is owned by MPS. It's got 6 40-liter tanks, and it's got an accompanying absorption train of 6 2-liter tanks. And it's been recently used in a great deal of work with various clients. Here is some pilot plant results on flotation concentrates. These flotation concentrates were assay at 20 grams per ton gold, 30 grams per ton silver, and 0.3 copper. They were being leached with 8 kilos of cyanide per ton, and the client's stated recovery was 88.5%. Now that's the horizontal blue line in the graph is our 88.5%, and the yellow line is the actual recovery that's taken from the carbon absorption tails. So that's a fire assay. And you can see for a goodly portion of the last of it, we're well over 90% in our recovery. And we're obviously dissolving gold that cyanide isn't dissolving on its own. So here's a table that shows something about the speciation of what happens. And in this case, we're able to show that in actual cyanide, we're able to reduce it by 77%. The cyanide in the tailings down to 0 by 100%. And you can can see the rest of the things. The WAD determination is down to about 100% under, from 2,500 down to 1%. And there's various decreases in other anions that you can see. You contrast this to concentrations of the International Cyanide Code. You can see that you can easily put it into tailings, and it's very close to being saying that you could put it, just discharge it as is. So that's quite a difference. Well, summing up, glycat is a dual lixiviant and oxidant process. It's able to reduce cyanide requirements by 50 to 80% on the ore. It's also able to recover the same or better gold extraction. It's able to recover copper as well as gold and silver. It's able to recover the leached gold onto activated carbon. And it's able to reduce cyanide speciation in the tails, so to reduce or eliminate the requirements for detoxification. Now for the whole paper in general, we can say that heated glycine and hybrid lixiviant systems such as glycine and non-cyanide additives are emerging promising alternatives to cyanide. The glycat process involves starved quantities of cyanide, has been demonstrated at pilot scale to produce a tailings well below International Cyanide Management Code recommendations without cyanide destruction. It offers a substantial reagent savings demonstrated to be 20 to 80%. It applies to complex gold ores and those with elevated base metals, as well as free milling ores. It's easy to adopt to existing CIL, CIP plants with little or no CapEx and implementation risk. It's nothing more complex than another tank to feed glycine. And if there's some questions about the process, you can revert to the old process very, very quickly just by turning off the glycine. So this implementation risk is taken out of it. There's no alteration. And our acidic GT process is under development as a potential method for treating oxidized refractory gold ores and acid leached copper oxide ores with residual gold values. So a final word about glycine. We have a glycine leaching technology project, and this can be applied to free milling gold ores, complex gold ores and concentrates, cyanides and oxygen consuming ores, refractory gold ores, gold tailings. We can offer a cyanide-free leaching option, and we're currently seeking companies that want to invest in the gold mining industry's future. My email address is on the final slide. Thank you for your attention to this paper. The virtual mode of the session prevents questions being asked now, but there is a panel session at the end of today, and I will be there on the panel, so save the questions for then. And thanking you again for your attendance. Good day.